Next, we want to look at a couple of concepts that are applicable to all states of matter. One of these is density. So density tells us how much mass is packed into a certain volume. So density is calculated by taking the total mass and dividing by the total volume. And for density, we use the symbol rho. So this is the Greek character rho. The units of density are kilograms per cubic meter. Sometimes if you look up densities in a table, instead of density, you'll be told the specific gravity of a substance. And the specific gravity is just the density of a substance divided by the density of water at 4 degrees Celsius, which is 1,000 kilograms per cubic meter. So with the specific gravity, you can multiply by the density of water and recover the density of the material. Pressure is another concept that we'll be looking at, and pressure is the amount of force divided by the amount of area that the force is exerted over. The SI unit of pressure is pascals, and 1 pascal is equal to 1 Newton divided by meters squared. So pressure makes a difference. This is the reason why you wear snowshoes in snow and not stiletto heels in snow. Under that heel, there's going to be a lot of pressure because a big force is spread out over just a tiny area, whereas snowshoes work by spreading your weight out over a much larger area and reducing the pressure on the snow to something that the snow can withstand. Next, we'll want to take a look at pressure within a liquid. So pressure, as you may know if you've ever done scuba diving, increases as you go deeper within a liquid. All portions of the liquid are at equilibrium. If the liquid is stationary in some container, it's not flowing anywhere, it's not moving. So all portions of the liquid are at equilibrium and they're all pushing against each other. And all points at the same depth are at the same pressure. So imagine that we have this rectangle or this box of liquid. So this is just an imaginary box of liquid that we've singled out as opposed to the rest of the liquid in the container. So we're just thinking about the liquid inside this imaginary box. So if we look at the forces that are acting on this imaginary box of liquid, and we're looking at the forces in the y direction, there will be a force exerted by the liquid above as well as a force exerted by the liquid below. And so the net force in the y direction will be the force, upward force exerted by the fluid below minus the downward force exerted by the liquid above, and then also minus the weight of the liquid itself. And so that's the sum of the forces acting on that imaginary box of liquid, and they will sum to 0 since the liquid is not accelerating. Well, these forces we can write as the pressure times the area, because if we rearrange our equation for pressure, pressure is force over area, multiply both sides by area, and you get that force is equal to pressure times area. So we can rewrite these forces as the pressure at level 2 times the area gives us the force, the upward force of the liquid below, and similarly with the downward force of the liquid above. Then we can also recognize the fact that the mass of the liquid is going to be equal to the density of the liquid times the volume. Here we've just taken the density equation and multiplied both sides by volume. So mass is density times volume, and the volume is equal to the area of the top of our imaginary box times y1 minus y2. y1's a little bit higher than y2, so y1 minus y2 will give us this height as a positive number. So then we can substitute this in for the mass in this expression, and we get this equation which involves pressures and areas that sums to 0. Then we notice that we have an area in each one of the terms, so we can divide everything through, including the 0, by area, and we get this expression here once we've taken and rearranged this equation. So we've taken the P1 and the rho times the difference in heights times g and moved it to the other side. So this is the final expression that we get, and this is the important one. So what this says is that the pressure at height y2 is equal to the pressure here times the density of the fluid times g times the difference in the depth. So basically what that's saying is that you have an increased pressure as you go deeper in the fluid, and that increased pressure is due to the weight of the fluid that's above you. So here's the expression rewritten once again, and we want to next consider a special case. If we are thinking about a container of fluid, and P1 is the pressure at the liquid surface, then that's going to be equal to atmospheric pressure. So if we have a container that is filled with fluid, we can find the pressure deeper within that container, and that's going to be equal to the atmospheric pressure that exists at the surface of the liquid plus this term that comes from the weight of the liquid pressing down at various depths. So the atmospheric pressure is equal to 1.013 times 10 to the 5th pascals. And this may seem like a big number, and it is a big number. And that's because you have a lot of atmosphere pressing down on the surface of any fluid. The atmosphere is actually heavy because there is a lot of it. So the atmosphere exerts an average pressure of 1.013 times 10 to the 5th pascals. This is also sometimes referred to as 1 atm, or 1 atmosphere, although 1 atmosphere is not the SI unit. The pascals number is, and this is at sea level. So if you go higher into the atmosphere, if you climb a mountain, then the pressure from the atmosphere will be a little bit less. So we can use that to rewrite this expression. So if we're looking at the special case of wanting to know the pressure at some depth inside a liquid, we can take the atmospheric pressure plus rho gh, where h is the depth that we're interested in finding the pressure, and then that will give us the pressure at that depth. So we can use these facts in order to come up with useful devices for measuring pressure. So this is a device which you possibly could have seen in something like a chemistry lab. This is known as a manometer. And a manometer is used to measure the pressure of a gas inside an enclosed bulb. So here we have a gas inside our manometer. We want to know its pressure, and we want to know its absolute pressure. So the key to finding the pressure is that this bulb of gas is connected to a tube that is filled with some liquid. Often that liquid is mercury, because mercury is nice and stable and it won't evaporate on us. So the manometer is filled with a liquid, and the key to using the manometer is to realize that according to our expression for pressures in a liquid, pressures at places at the same height will be at the same pressure. So since A is at the same height as point B, these 2 points are at the same pressure. The pressure is the same everywhere in a gas. A gas will always flow to equalize its pressure. So the pressure everywhere, including point A, is the pressure of the gas. But point B, since it's touching the liquid like point A is touching the liquid, is at the same pressure as point A. So that means point B is the same as the pressure of the gas. So that's expressed here. The pressure of the gas is the pressure at point A, because point A is in contact with the gas. But since point B is at the same height and both point A and point B are in contact with the same fluid, then point B is the same pressure as the pressure of the gas. And that pressure, since it's at a depth beneath the surface of the fluid that's open to the atmosphere, is equal to the atmospheric pressure plus rho gh, where rho is the density of the fluid and B is the depth of this point beneath the surface of the fluid. So then, if you want to measure the pressure of the gas, all you need to do is see how high this column of fluid is, So if once you know how high the column of fluid is and you know the density of the fluid, you can add that to the atmospheric pressure and find the pressure of the gas. Now, one thing to keep in mind that we will run into with problems is that sometimes in a problem you are told what the absolute pressure is. Sometimes you're told what the gauge pressure is. And the gauge pressure is equal to the absolute pressure minus the atmospheric pressure. So for example, if you were to take a football and take a pressure gauge and measure the pressure of the air inside the football, you would get the gauge pressure, not the absolute pressure. So what you're getting is the difference. You're seeing what is the increase in pressure inside the football as opposed to the atmosphere outside the football. The same thing with a tire gauge for your car. The tire gauge gives you the difference between the pressure inside the tire and the atmospheric pressure outside the tire. And so if you ever want to know the absolute pressure, so for example, if you're using something like the ideal gas law, that requires you use absolute pressures. And so you would need to convert gauge pressures to absolute pressure by adding atmospheric pressure in order to use that pressure in something like the ideal gas law. Another tool for measuring pressure is a barometer, and a barometer actually measures atmospheric pressure because atmospheric pressure isn't always 1.013 times 10 to the 5th pascals. That's the average pressure at sea level. But you may not be at sea level, or also changes in weather can cause slight variations in that atmospheric pressure. And so a barometer measures those changes. So the way a barometer works is that you have a tube which is mostly but not completely filled with a fluid such as mercury, and then there is a dish of mercury down here which is open to the atmosphere. At the top you have the glass tube. The top of this glass tube is completely evacuated. All of the air has been sucked out, and so the pressure up here is equal to 0. So then once again we use the fact that the pressures at the same level that are touching the fluid are at the same pressure. So point A, since point A in the fluid is on the surface of the fluid, it's open to the atmosphere, so point A is at atmospheric pressure. But if we look inside the column, at this location here, this is also at height A, so it's at the same pressure, and that pressure is equal to the pressure at the top of the column of fluid, which is 0, plus rho GH, where rho is the density of the fluid and h is the height of this column of fluid. So since we know this pressure is 0 at the top, and the pressure at the top plus rho GH is equal to the pressure here, we can measure the height of the column of mercury and multiply it times G times the density of the mercury, and that will give us the pressure here, which is also the atmospheric pressure. So we can directly measure the atmospheric pressure and changes in the atmospheric pressure. So next let's look at this example problem. So in this example we have a 15,000 Newton car on a hydraulic lift. It rests on a cylinder with a piston of radius 0.2 meters. If a connecting cylinder with a piston of 0.04 meters radius is driven by compressed air, what force must be applied to the piston to raise the car? So this is looking at how hydraulic lifts actually do work. So the most important thing with this is to draw a picture showing how the hydraulic lift is working. So with this hydraulic lift, you have two cylinders. You have a small cylinder, and this is the cylinder upon which you exert the force. So you have a downward force driven by the air compressor, and this downward force, I'll label it as F1, and then this is a small cylinder and it has a cross-sectional area which I'll call A1. Then there is a second cylinder which is much bigger, and this is the cylinder that the car rests on. So here we have a cylinder, and on this cylinder is our car. So the car is here resting on this cylinder. And this is a bigger cylinder. So this cylinder has a cross-sectional area of A2. Now the key is that both of these cylinders are connected by a fluid. So you have a channel of fluid. So here's one side of that channel, and then here is the other side. So this channel is completely filled with some fluid. So there's all this fluid connecting the two cylinders. And the other thing we know is that these cylinders are at the same height. And since they're at the same height and they're touching the same fluid, they're at the same pressure. So we can say that the pressure at the bottom of cylinder 1 is equal to the pressure at the bottom of cylinder 2, since both of these cylinders are at the same height and they are touching the same fluid. So they have the same pressure. We know that pressure is equal to force divided by area. So the force being exerted here, downward here, divided by the area, that's creating the pressure on this side, and that's going to be equal to the force of the fluid on this cylinder. So that's F2 over A2. So then what we're interested in is F1. How much force do we have to apply with our air compressor? Because we push down on the air compressor, that creates some pressure here. The fluid delivers that pressure, and then there's going to be this upward force, force 2. So how much do we have to press with the air compressor? So I'll rearrange this equation by multiplying both sides by A1. And so F1 is equal to F2 over A2 times A1. So then we can start plugging in numbers. So F2, that's the force that this cylinder has to support, which would be equal to the weight of the car. If we're supporting the car with the lift, we have to be able to support the car's weight. And so that's going to be 15,000 newtons. A1 is the area of piston 1. So since that's a circle, that's going to be pi r squared. So that's pi times the radius, which is 0.04 meters squared, divided by A2, and that's pi times the radius of the big cylinder, which is 0.2 meters, and then that also gets squared. So F1 is going to be equal to 600 newtons. So as long as we apply a force that's greater than 600 newtons, we will be able to lift this 15,000 newton car. It kind of feels like cheating, but that is what happens when you compress or try to compress a fluid. The fluid just transports that force to the other side, and it transports it keeping constant pressure. So now let's look at this second example question. So for this example, we have a container filled to a depth of 20 centimeters with water. On top of the water floats a 30 centimeter thick layer of oil with a specific gravity of 0.7. So what is the absolute pressure at the bottom, the very bottom of the container? So once again, we'll draw a picture of this scenario. So we have this container, and the container has two fluids in it. So the first fluid is going to be the water. And so the first fluid is the water, and we know that it's filled to a depth of 20 centimeters with the water, and then on top of that is floating another fluid, which is the oil, and the oil is filled to a depth of 30 centimeters. And what we want to know is what is the pressure down here at the bottom of the water. So at the surface of the oil, we know that here we have atmospheric pressure because there's only atmosphere above the surface of the oil. So this will be at atmospheric pressure. Then at the bottom of the oil, I'll call that P1, the pressure at the oil-water interface. And then what we want to know is what is P2, the pressure at the bottom of the water. So we'll tackle this in steps. So first off, let's find the pressure at the bottom of the oil. So we know that if we want to find this difference in pressure, then the pressure at point 1 here at the bottom of the oil is equal to the atmospheric pressure plus rho for the oil times G times the depth of the oil. So we need to figure out what is the density of the oil. And we're not told the density, instead we're told the specific gravity. But we know that it's easy to convert between specific gravity and density because the specific gravity, which is 0.7, is equal to the density of the oil divided by the density of water. And we know that, or we can look up easily what the density of water is. So actually, the density of the oil is equal to 0.7, then the density of water is 1,000 kilograms per cubic meter. So that means the density of the oil will be 700 kilograms per cubic meter. Okay, so then we can plug those numbers in. So the density at point 1 is going to be atmospheric pressure, 1.013 times 10 to the 5th pascals, plus the density of the oil, 700 kilograms per cubic meter, times G, which is 9.8 meters per second squared, times the depth of the oil, which is 30 centimeters or 0.3 meters. So that's going to give us a density at the bottom of the oil that's equal to 1.0336 times 10 to the 5th pascals. All right, so now that we know the pressure here, we can find the pressure at the bottom of the water by comparing it with the pressure at the top of the water. So P2 is going to be equal to P1 plus the effect of the water, rho for the water, GH, where H is the depth of the water. So we know that the pressure at the top of the water is 1.0336 times 10 to the 5th pascals, and we add to that the density of water, which is 1,000 kilograms per cubic meter, times 9.8 meters per second squared, and then times the depth of the water, which is 0.2 meters, or 20 centimeters. So then that will give us a final density of 1.05 times 10 to the 5th pascals, and that would be the pressure at the bottom of both the oil and the water. So here is another question. Looking at this set of kind of crazy tubes that are all open to the atmosphere, where would the pressure be the greatest?